Good day, everyone. You are welcome to today's lesson. The topic is simple harmonic motion. It's a revision guide because it's not a new topic. Many of us, all of us must have heard this before at one point or the other. But I'm aware that a number of us still have issues with it. So that's why I brought this topic again today so that you have a better understanding of it. By the end of this lesson, you should be able to do three basic things. One, you should be able to define simple harmonic motion. And by defining it, I mean that you should be able to tell us the key features of simple harmonic motion, particularly differentiating it from your linear velocity, your linear motion. Secondly, you should be able to calculate the different things you will need to calculate as it relates to SHM. You have to know how to calculate your angular velocities, angular acceleration, calculate your period, your frequency, and to define these terms also. And then lastly, you must be able to tell the different kinds of oscillations that we could have under SHM. These things are very important. I can guarantee you that if you master this topic well, you will at least have mastered one topic that is sure to be faced in your upcoming exams. So let's go on the journey. As we go on, you'll be solving some questions. So I hope your calculators, your pencils, and erasers and biros are nearby. Firstly, what do we mean by simple harmonic motion? Any definition of simple harmonic motion must have four things, four features. One, it is the motion of an object about a fixed point. What does that mean? The motion of an object about a fixed point. That means essentially it is a periodic motion. It's when an object goes to and fro, or up and down, or oscillates, moves in circles, where a point acts as the center of oscillation. So movement about a fixed point is very key when defining simple harmonic motion. Then two, the acceleration of that object is always directed towards that fixed point, that mean position. So that acceleration, all of us will remember that acceleration is a vector quantity. It has magnitude and direction. But in this case, the direction is fixed. So under simple harmonic motion, you cannot change the direction of the acceleration. The direction of acceleration is fixed towards the fixed position. That is the center of oscillation of that object. Thirdly, that acceleration is directly proportional in magnitude to the displacement of that object from that mean position. So what does that mean? Magnitude refers to value, the value you ascribe to a quantity. If you say you weigh 50 newtons, for instance, 50 is the magnitude. So in essence, we are saying that the value you will get for the acceleration will increase as the distance between the mean position or the center of oscillation and where your object is. As that distance increases, then your acceleration will also increase. That's why acceleration is always proportional to the displacement of the object from the mean position. And then the last point that must be there, the acceleration and the displacement are always in opposite directions. That means that if you have already said the acceleration must always be towards the mean position, that's where it must be directed. That will tell you that the displacement must always be directed away from the mean position. Both of them cannot be in the same direction. So let us not miss that. So from what you can see on your slide, definition of SHM is a periodic back and forth motion of an object about a fixed point, such that its acceleration is always directed towards the mean position. Acceleration is directly proportional to its displacement in magnitude from that point and opposite in direction to the displacement. I want you to allow that one to sink in for about 2 seconds. Good. Looking at your slide, you can see one bulb going to and fro, and then right above that, you can see a spring, a stretch spring. I have deliberately put these two here to let you know that whenever simple harmonic motion is being discussed, these two scenarios are more often than not what we use as our benchmark, what we refer to. So it's either a spring that is oscillating to and fro, back and forth, or a pendulum bob going to and fro. Now, under SHM, there are some terms that are used. Some of these terms are also used under another topic, which is waves in physics. The good thing is they mean the same thing, whether under waves or under SHM. One of the terms is a period. Period is a time taken for one oscillation, or period is a time taken to go through one cycle. One cycle. So in essence, period is time, but it is a specific time. It is not just a random time. So when you are dealing with period, then the number of oscillations there is just one. If your object is completing 20 oscillations and they are giving you the time for that 20, that time that you were given is not the period, because that time is the time for 20 oscillations. But period is a time for just one oscillation. And like any time measurement that we have, it has a unit, which is seconds. Then we have the frequency also. Frequency is essentially the inverse of period. Frequency is the number of cycles completed per second. It is measured in hertz, or cycles per second, or if you like, oscillations per second. Whichever you need to decide to put, you will be right. But the person that has that first worked on this is Heinrich Hertz, and decided to put his name there as a unit. Maybe to immortalize himself. That's good. And then I have to stress something here. There's a difference between angles of oscillation and numbers of oscillation. There's a difference. That is where many students mix it up. If I say that an object goes round a circle 20 times, it has not covered 20-degree angle. It has only gone round a circle making 20 oscillations or 20 cycles. That 20 is not the angle, it's not the degree. Why? Because the angle that you have in a circle is 360 degrees. So if you go around the circle 20 times, you have gone around the circle 360 times 20. So please do not use number of oscillations as angle of oscillation. And I have to stress that because by the time you are calculating angular velocity, this could become a problem. Now the question will be, sir, if I have my number of oscillations, how do I then convert it to angle? I already said it. 360 degrees is the angle for one complete oscillation. That means that if you have gone around a circle once, or you have moved to and fro, maybe like a pendulum board that has gone to and fro one time, it has made one oscillation, that is 360 degrees. And then, as you probably remember, our angles in SHM, we don't measure them in degrees before we saw. So we must convert the angles that we have in degrees to radians. And that one is simple to do. Just remember that 360 degrees will give you 2 pi radians. So if you have 180 degree, that will give you 1 pi radians. If you have 90 degree, that will give you half pi radians. So whatever degree you have been able to calculate, just use your benchmark of conversion of degree to radian to get what it will be in radian. So let's move on. We have defined the terms. Now I want us to look at the specific case of a spring. Incidentally, there's one topic in physics also that serves as a foundation for this. That's Hooke's law. When you have a spring that extends, when you apply a load to it, and the extension is proportional to the load you apply, we say that spring obeys Hooke's law. Now, the to and fro movement of spring, as described by Hooke's law, is also a very good example of SHM. Because when the spring goes to and fro, it has fulfilled everything that we need to do, every feature that SHM must have. There's a to and fro movement, that's a periodic movement. Acceleration is directed towards the mean position. It is proportional in magnitude to the displacement, in this case, the extension of the spring. Now, you will see that we usually use negative force, negative sign to describe our force or our acceleration. Why? Because the force or the acceleration under SHM is a restoring force. And what does restoring mean? It's a force that acts in opposite direction to displacement. So anytime you have an acceleration or a force that acts in opposite direction to displacement, that force is a restoring force. So you may have to pause here and look through the slides again so that you can get a grasp of all that we are doing. If you look at the diagram on your screen, you can see the first string, the unstretched spring. The spring has an original length. Then you have, by the time you stretch it, you apply a load F on it. You can see that it stretches a little. It stretches to a distance X. When you increase that load F to 2F, it stretches to a distance 2X. Now the spring constant, that is the amount of force or you must apply on a spring for you to have an extension of 1 unit. That is what the spring constant is. Those of us, if we have all done our Hooke's law, we can refer to it again to give us a very good understanding of that. But I'm relating this with SHM. Now, from what we have done so far, here is an example which you are going to finish up yourself. I have done it halfway for you and I've even given you a hint. I want you to look at this example and attempt it. The hint here is that we have two forces that are equal to each other. We have the force that creates the acceleration on the object, and we have the force that creates an extension. That's why I put a hint there. I said that since F equals Kx, and F is also equal to ma, then your Kx must also be equal to ma. Kx must also be equal to ma. Let us not forget that. If you do it well, you get your answer as 180 newtons per meter. Please take note. Hint, Kx is equal to ma. Kx is coming from our Hooke's law. Ma is coming from our normal formula for force. Let us now go to energy and simple harmonic motion. Just like every object that we have, they all possess energy. So also springs also possess energy. A spring has potential energy when it is stretched or compressed, which we refer to as elastic potential energy. A stretched or compressed spring can do work due to this elastic potential energy. It can work, can do work. Now, this elastic potential energy can be converted to kinetic energy, which is changed back to potential energy when the object reaches a momentary rest position. This is just the essence of conservation of energy, changing from one form to another. In this case, from elastic potential energy to kinetic, back to elastic potential to kinetic again, and on like that. So let's look at conservation of energy in springs. First, formula for elastic potential energy, half kx squared. The x here stands for displacement, please, not length. Not length, not original length, but displacement. Displacement means difference in the length. There was an original length, and then you apply the load, you now have a new length. The difference is them, is what the X stands for. Please take note of these things here. Now, let's now look at another instance of SHM. That's a pendulum. Pendulums, like springs, move back and forth, exhibiting simple harmonic behavior. A simple pendulum consists of a particle of mass m attached to a frictionless pivot P by a cable of length L and negligible mass. That string is what has negligible mass. That cable is what has negligible mass, not the bulb itself. The mass of the bulb is not negligible. Please take note. And to relate your period of a pendulum bulb to your length of the string or the cable and the acceleration to gravity, the formula is 2 pi square root L over G. Take note of the square root. The square root must cover the entire L divided by the G. Please take note of that. Now we have another example here, which I want you to use the formula we just looked at in case you do not remember that formula. T equals 2 pi root L over G. So I want you to solve this question by yourself. Good. So here is the solution. T equals 2 pi root L over G. You are asked to find the height, that's the length. If you do it well, your answer will be 21.93 meters. Now, useful formulas. We are rounding off very shortly. Useful formula for SHM. These are just to bring some of the things that we have already looked at. Formula for springs, for periods of springs, for the ones for pendulum bulbs, we have them here. For spring, T equals 2 pi root M over K. M is the mass of the object, K is the spring constant. For pendulum, 2 pi root L over G. And then our angular velocities, we also have their formulas here, just to remind us. Velocity and acceleration of pendulum at displacement X. We also written the formulas here, just to also remind us. And let us also not forget that for a pendulum bulb, the maximum energy of a pendulum bulb is experienced at the mean position. That's where there's the maximum velocity and no height. Finally, we have types of oscillations as we round up. We have the free oscillation. Free oscillation is the type we have with our pendulum bulbs, where you just hang your bulb and it begins to move about a mean position. That's the free oscillation. Damp oscillation is a kind of oscillation also that you have, but in which there is something or a substance that is reducing the amplitude of that oscillation with time. An example is when you have a loaded spring that is vibrating in a liquid. That liquid will resist that vibration with time. Forced vibration, this is when one body sets another body into vibration. That means you have a body vibrating, and because it's vibrating, maybe it strikes another body or it hits another body, and then that second body now begins to vibrate. That's a forced vibration. And then we have resonance. Resonance is also a type of forced vibration, but in this case, both bodies will vibrate at the natural frequency of the body that has been set into vibration. That is a frequency called resonance frequency. We may have to go back and read up on these slides again for better understanding of this. So that is where we end the lesson for today. But you have tasks that you have to do, which I will expect in the next 72 hours maximum, 72 hours maximum. And do them is given to you here in the videos. Do them. If you need to refer to the video again, please do and solve this and then turn it in. You are to send the responses to this assignment to my email within 72 hours. My email is david.oluwadara@olashoreschool.com. david.oluwadara@olashoreschool.com. Thank you.